We're going to talk about the freak. We're going to talk about the freak water. But first, a little water joke. You're familiar with the water molecule there with its two hydrogens and its one oxygen, I believe. So, if water is H2O, then what is H2O4? You know, it's for bathing and drinking and stuff like that. Okay. Water molecules are crazy, and water as a compound has a lot of amazing and unique properties. And all the properties that we're going to talk about and that we're going to experiment with in lab are related to the polarity of water molecules. So, water molecules are polar, like any molecule that's polar, because there's an uneven distribution of electrons in the molecule. So, if all the positive and negative charge in a molecule is evenly distributed throughout the molecule, it would be nonpolar. When there is not an even distribution of the charge, it would be described as polar. So, what's that? What does it mean if something is polar? Well, you're familiar, I think, with magnets having a north and a south pole like the Earth does. And magnetically, north and south are opposites. And that's what polar means. It just means that something has two sides. It has opposite sides. In the case of molecules, they have opposite sides in terms of their electric charge. They have a positive and a negative side. All right, our water molecule is polar. It has a positive and a negative side. The negative side is the oxygen side on top of this diagram. And because both of the hydrogens are kind of positive and they're both on the same side of the molecule, that side is the positive side. So very distinctly positive and negatively charged sides. And that happens because the atoms involved in the water molecule, the one oxygen and the two hydrogens, they're covalently bonded, which means they're sharing electrons, but they ain't sharing them equally. Oxygen has a very strong attraction for electrons. Hydrogen, not so much. So the electrons that are being shared by the oxygen and by the two hydrogens in the covalent bonds of this molecule, those electrons are not being shared equally. So they spend much more time over by the oxygen side than they do by the hydrogen side. And so overall, the molecule has this positive and negative quality to it. The symbols here that you see are ones that chemists and physicists use to describe a partial charge. That is the lowercase Greek letter delta, and it means partial. So partial negative charge on the oxygen side, partial positive charge on the hydrogen side. So, because an individual water molecule has a distinctly positive and negative side, if you get a whole bunch of water molecules together, they are going to naturally attract each other. Opposite charges attract. Positive charges positive attract to negative. So for the water molecule in the middle here, the hydrogen part of that molecule is kind of positive. The oxygen part of another water molecule is kind of negative. And there's going to be a quite strong attraction between the positive and negative sides of those two molecules. This special kind of polar attraction between molecules in water and in other compounds is particularly strong and particularly important in terms of chemistry and how these substances behave, what their characteristics are. So we give it a special name. It's called hydrogen bonding. And it always involves an atom like oxygen with a super strong attraction for electrons bonded to a teeny tiny hydrogen atom. And when that happens, it sets up this positive and negative polarity that allows for a hydrogen bond to occur. And because of that hydrogen bonding, because of the really strong attractions between water molecules, it has some unique and amazing properties. First, water is very cohesive. Cohesion is when a substance, the particles of a substance, attract the same like particles. So the attraction between the water molecules that we saw in this slide, that's cohesion. And because of the cohesiveness of water, and because of the unique situation that happens at the surface of water, there is an extra strong attraction that gives water and other liquids this property called surface tension. It's like a skin on the top of the liquid. And because the cohesion in water is super strong, this surface tension effect in water is very pronounced. You see the spider standing on the water there. And then this picture on the left, one of my favorite science pictures of all time. A coin dropping it into water, seen from the side. And you see how the coin is like fallen down and stretched, like the water really had a skin, stretched the surface of the water down. And now this is all air in here, and the water has yet to collapse back on itself and create the new surface as the coin falls down below. Cool stuff. All right, adhesion is also an important property of water. Water molecules not only stick to each other very strongly, they will stick to any other polar compounds, any other polar molecules. And plants and the cell walls that make up plants are made out of a substance that is quite polar. And plants take advantage of water's stickiness, and they build tubes, tiny microscopic tubes that allow water to go up against the force of gravity, even in the tallest trees, 100 meters high. Water is carried from the roots up to the leaves without a pump, without any energy being expended, just because the water sticks to itself so much, so strongly, and sticks to the walls of the xylem vessels. We'll talk about that later on, and sooner than later if you're interested. Water has a really high specific heat capacity, and again, this is related to the stickiness of the water molecules, the cohesion. For the temperature of something to go up, the particles have to be moving faster. Because water molecules are so strongly attracted to each other, they're all stuck together, and to get them to move faster, you kind of have to unhook them from all of the attractions that they have for other water molecules. Well, that means you have to add a lot more energy to break all those attractions and get them to move around faster. So it takes a massive amount of energy to change the temperature of water just a little bit. And this is why at the beach on a sunny day, the sand can be super duper hot, and you run down to the water and the temperature hasn't changed, maybe a degree or two from overnight. And experimentally, we're going to look at this in lab, but the diagram over to the right shows you quantitatively how big this difference is between water and most other substances. If you add the exact same amount of energy to 100 grams of water compared to 100 grams of iron, the temperature of the iron will go up 20 degrees to only 1 for water. So it takes 20 times the amount of energy to change the temperature of water compared to iron, to change it an equal amount. Water when it freezes and becomes solid, that's ice to us, it expands. It becomes less dense. And this isn't a totally unique property to water. There are other substances that exhibit this property, but it is unusual, and it's absolutely essential for some life on Earth, like the seal and her pup there, because there are lots of places on the Earth where in the wintertime the temperatures are so cold that the surface of lakes and ponds and the sea freezes over. And if water wasn't less dense in its solid form, we wouldn't have this effect of ice creating a layer like a blanket, an insulating layer on the top of those bodies of water and allowing the liquid water to remain below so that the aquatic life and the marine life that lives there can survive those winters. Finally, a little bit about water as a solvent. Water is really great at dissolving stuff, and that's because it's attracted to most things because of its polarity. But to add some meaning to this, let's introduce a term, chemical mixtures. A mixture is when we have more than one substance mixed together, but they are not chemically bonded to each other. Like you can put hydrogen and oxygen together and they can chemically react and make water, H2O. But you can also just mix hydrogen gas and oxygen gas and they don't react, and then you just have a mixture of hydrogen and oxygen. So mixtures of chemicals are important. We are giant bags of mixtures of chemicals. So a solution is one kind of mixture, and it's a mixture that has a homogeneous distribution of the substances in that mixture. Solutions make up the basis for the substances inside of a living thing, in the cytoplasm, in the blood, in the extracellular fluids that make up the bodies of organisms. Those are all solutions, and the substances that we need to survive are dissolved in the water that makes up the majority of our bodies. And I'm going to leave it at that. That's enough for this video. That's enough of me talking. I'll see you all soon.